Alright, so we're continuing with our trigonometric substitution. Now I've done the first three formulas with the previous group, and I will redo it with you all. Now the first three that we dealt with was the first three that I gave you on the table here. And this was number 4. Right, so now this one you will not find in the N5 textbook, but it is in the formula sheet. Right, this formula. Now, how do they get from here to here? Right, so you can use partial fractions. Right, you can use partial fractions here. You can separate this into, this can be factorized. Right? Can you see that? It can be factorized. But now what happens if you try and use a trigonometric substitution? Right, so where there's square roots, we have to use a trigonometric substitution. Right, so if I want to use a trigonometric substitution here, then what I'm going to do is, okay, so this is the formula. Right, so now let's see how we get from here to there. So if we can do it with the formula, then we will do it with any example, because what will change in the example? Just that this will be a 2 squared, 3 squared, or whatever it is. Alright, so now, here, I can let x equal to a sine theta. Now, right, so the sine theta substitution, the sine substitution is normally when you have a square root of a squared minus x squared. Because what is the aim here? The aim is when you have a square root, to get rid of the square root without actually squaring it, is to have something like this here, the square root of maybe 4. Now, without actually squaring it, I can get rid of the square root because the square root of 4 is 2. Can you see that? So maybe if I have the square root of 16, the square root of 16 will be 4. I'm only taking the positive. So the square root of sine squared will be sine. Okay, there's actually two possibilities, and I'm just taking the positive here. Right, now. So the substitution that we used when we had this one, when we had 1 over the square root of a squared minus x squared, was a sine substitution. Okay. But now there's no square root. What happens if you actually do it? So if I let x equal to a sine theta, then what will happen now? I go dx d theta. The derivative of a sine theta will be a, well, a represents a number. That's going to be a cos theta. This is the actual substitution. Remember we did use substitution previously? This is trigonometric substitution. So if I make dx the subject of the formula, then dx is equal to a cos theta times d theta. Remember we always make dx the subject. Now, so what do we have here? We have dx all divided by a squared minus x squared. So now what am I doing? I'm going to replace, there's my dx, well there's a 1 here. So the dx is a cos theta d theta. Then in the denominator, I have a squared minus x squared. But what is x now? X has been replaced with a sine theta. So that's going to be a sine theta all squared. So now I have a cos theta d theta. And then I have a squared minus, if I square this now, these are two factors here. So I will square it, that's going to be a squared times sine squared. Can you see that? It's going to be a squared times sine squared. Now remember when you square every factor there. Now what do you notice? A squared and a squared is common. That's why I have to let x equal to a sine theta. So I can have both a squared and a squared as a common factor. So if it is a common factor, let's see what happens when you take it out. So what I'm going to do is I'm going to take out a squared as my common factor. So if I take out a squared, I'm left with 1 minus sine squared. Can you see that? So I took out a squared times 1 is a squared times minus sine is minus a squared sine squared. Now we took out the common factor of a squared, so we can get the square identity 1 minus sine squared. Okay, now, so on the top I have a cos theta d theta, and in the bottom I have a squared, and I know that 1 minus sine squared is cos squared theta. So now I can simplify this, yeah? So I have a divided by a squared, which is 1 over a. You're clear with that? There's a on the top, divided by a squared, a will cancel, that's 1 over a. Here, cos divided by cos squared will be the same as 1 over cos. Right, so because cos will cancel in the numerator, now I need to integrate 1 over cos. So I've got my 1 over a there. So 1 over cos, using your identities, 1 over cos is equal to sec theta. Alright, so now we need to integrate sec of theta. So what is the formula to integrate sec theta? Now you can go to your formula sheet. So to integrate k sec bx, the answer will be ln of sec bx plus tan bx all divided by b plus c. That is how you integrate sec. You can check your formula sheets. It comes from the exact derivatives f prime x over f of x. But we won't go into the explanation of that now. You just take it for granted that it's given to you. Right, so now I want to integrate sec of theta. So the answer will be ln absolute value of sec theta plus tan theta plus c. Remember, you might be wondering that's bx, so it's actually 1 theta. So that's 1 theta all over 1. I don't have to write down the over 1. Alright, my coefficient is a positive 1. Now, let's see what we have here. Now, I got my 1 over a, I got ln. Let's look at the answer. The one that's on the formula sheets. I got 1 over a and I got ln. There's my 1 over a and I have ln. I don't have the 2 and I need to get back now. Remember, I used a substitution. I let x equal to a sine theta. So now I need to get sec theta back in terms of x and tan theta in terms of x. So how do we do that? Right, so if we go back to our original substitution, then x is equal to a sine theta. Right, let me do it here. So I know that, okay, let me just write it down here. It's sine theta is equal to x over a. If I make sine theta the subject of the formula, can you see that? So sine theta is given as a fraction or as a ratio. It is opposite divided by hypotenuse. Remember your SOHCAHTOA? If sine is defined as the opposite side divided by the hypotenuse side in a right angle triangle. Right, so I'm dealing with only positive values here. So let's draw our right angle triangle in the first quadrant. It's a simple right angle triangle here. And let's call this theta. Right, so now I've got sine of theta is opposite divided by hypotenuse. So the side opposite theta is x, and the hypotenuse opposite, which is x, hypotenuse, which is a. So there's my a. Can you see that? Now, okay, what do I want? I want sec. I will explain to you sec now. But remember, if we have two sides of a right angle triangle, I can find the third side by Pythagoras. Right, so let me call this P, Q, R, and if I use Pythagoras, then the square of the hypotenuse, the theorem of Pythagoras states the square of the hypotenuse, which is a squared, is equal to the sum of the squares of the other two sides. So the other two sides are, so x squared plus, I'm calling the unknown side QR squared. You're clear with that? My unknown, I'm just calling it QR. So the square of the hypotenuse is equal to the sum of the square of the other two sides. So therefore, a squared minus x squared is equal to QR all squared. So we are in the first quadrant, x is positive, so I'm taking the positive square root of a squared minus x squared is equal to QR. I found the square root of both sides. We cannot go any further. There's a minus sign separating the terms, so you cannot find the square root of a squared. You cannot find the square root of x squared if there's a minus or a plus separating terms. Right, so now what did I just do? I found out that QR is the square root of a squared minus x squared. Now that I have that, so what do I know now? I know the opposite side is, opposite theta is x. I know that adjacent theta, the side next to theta, is the square root of a squared minus x squared, and I know that the hypotenuse is equal to a. Right, now, so katoa, sine is opposite of hypotenuse. The question is, okay, let's look at something you're familiar with, tan. What about tan? Tan, if I go tan of theta, so katoa, tan is opposite over adjacent. So opposite over adjacent. Can you see that? Or there's it on the diagram here. Opposite over adjacent. Same thing, just that I wrote it down nicely there. So my opposite side is x and adjacent is the square root of a squared minus x squared. I now have a substitution for tan theta back in terms of x here. Can you see that? Now I need a substitution for sec. So in order for me to know sec, I need to know cos, because remember that cos theta is equal to adjacent divided by hypotenuse. That's ka, C-A-H, so katoa. So if cos is adjacent of hypotenuse, therefore sec theta will be hypotenuse over adjacent. Remember identities, cos is 1 over sec, sec is 1 over cos. Swap numerator and denominator, and there's my sec. So, what is sec? Hypotenuse. What is the hypotenuse? It is a over the adjacent side, which is the square root of a squared minus x squared. Right. So now I'm done with the problem. It's just about substituting back. So that's going to be 1 over a ln sec theta, which is going to be a all divided by the square root of a squared minus x squared plus tan theta, which is x all divided by the square root of what is it, tan theta of a, same thing, a squared minus x squared plus c. What do you notice about the denominator? Yeah, the denominator is common. Can you see that? Right, so now let me just write it with a common denominator. So this is equal to 1 over a ln absolute value. My denominator is common, which is the square root of a squared minus x squared. And then I got a plus x on the top there. Right, so now The formula still doesn't look like this here. This has a square root, that does not have this. That has a square root, there's no square root here. Can you see that? Now it's all about simplification. Right, so I'm going to simplify this further. So watch how this is going to be simplified. I got 1 over a ln, then I got my a plus x there, and I got the square root, and I noticed that a squared minus x squared is the difference of two squares. So this can be written as a minus x, a plus x inside the square root. I'm factorizing, can you see that? Now, that means this, remember, if I have exponents, if I have something like the square root of 25 times x squared, this can be split up into the square root of 25 times the square root of x squared. It's multiplication, exponent laws. So what I'm going to do here is I will write it as the square root of a minus x times the square root of a plus x. Okay, now I'm going to go further. Alright, so here I got a plus x, and this is the square root of a minus x, and this is a plus x to the power half, and on the top it's a plus x to the power 1. Can you see what I'm talking about? Right, so now it means I can simplify this further by using my exponent law. Remember, my exponent law is if I have x to the power a all divided by x to the power b, when the bases are the same and its division, I can write down my base once and I go top minus bottom. So therefore, let me just write this with to the power half too. Okay, so that's a minus x to the power half. Now, this I did not interfere with. Here the bases are the same. A plus x and a plus x within brackets, the bases are the same. So if I write down the base once and then I go top power, subtract the bottom power, 1 minus half is what? 1 minus half is half. What do you notice now about the powers? They are the same. So now, going back again, a lot of exponents involved here. So if I have something like 2 squared divided by 3 squared, what do you notice about the powers here? They are the same. So this can be written as 2 over 3 all squared. So that means this can be written as a plus x all divided by a minus x, just like how I got 2 over 3 all raised to the power half. Exponent law. Can you see that? Now, what else? One more final thing to do. If I have something like log of 4, we know that log of 4 can be written as log of 2 squared. We know that log of 2 squared can be written as 2 log 2. Now, the point I'm trying to make here is that if you have a power, you can bring down that power. Can you see that? So what does it mean now? That means this power of half, I can bring it down in front here and it becomes 1 over a times 1 over half. That's exactly what I'm going to do now. So it becomes 1 over a times 1 over half ln of a plus x divided by a minus x plus c, and that becomes 1 over 2a ln a plus x divided by a minus x, and that is how we get the formula. Where's it here? By using trig substitution. This is formula number 4. So here in N5, okay, you might get a question like this, but 99% of the time you're just applying the formula. But if you're going to DUT or any university of technology, when you're doing this section, you do it exactly like how I'm doing it on the board here. Right, so this is formula number 4. I'm going to show you the next one now. Right, let's take formula number 5. Formula number 5, again, not in the module, the textbook one that I showed you. So, but this is in the formula sheet. So here, there's actually 2. It depends on which one you're using. Depends on the question that you get. It's either, it could be x squared plus b squared, or x squared minus b squared. Okay, so in a situation, I'm just taking the minus as an example to show you. Okay, so now, we know now that U substitution does not work over here. I'm talking about if you did not know the formula. Okay, U substitution here does not work because there's no exact derivatives here. That's why we use trigonometric substitution. Alright, so now, in the previous example, I had 1 minus sine squared, which is cos squared. Okay, so now, here, if I go and let x equal to, let's say, b sine theta, then I'm going to have sine squared. I'll take out b squared as a common factor. You know that's going to happen. The problem is I'm going to have sine squared minus 1 here. Sine squared minus 1 is not cos squared. You need 1 minus sine squared. So if this was the other way around, then like formula number 3, then I will use a sine substitution. So which identity can I use that will allow me to get rid of the square root? Okay. So if you remember the identity 1 plus tan squared of bx. What is 1 plus tan squared of bx? It's equal to sec squared bx. So I know that tan squared bx is equal to sec squared bx minus 1. Okay, so the idea here is to have sec squared minus 1 inside the square root. So once I have sec squared minus 1, it will equal to tan squared. Then I'll have the square root of tan squared, which will cancel the square root will cancel. So that is the whole idea for this type of one. We are going to be using a sec substitution, this one here. Okay, so what I'm going to do here is I'm going to let x equal to b sec theta. You know I have to include the b, otherwise I won't have b squared there. I won't be able to take out a common factor. Right, so if x is equal to b sec theta, then I know that when I need to also make dx the subject, get dx in terms of theta. So dx d theta, the derivative of b times sec will be b sec theta tan theta. So therefore, if I make dx the subject of the formula, it's going to be b sec theta tan theta times theta. Alright, so let's do the substitution. So this is going to equal to the integral of the square root of x. There's my x here, which is b sec theta. So there's my b sec theta all squared minus b squared. So there's a germ, x squared, b sec theta squared minus b squared, only dx, there's dx here. So my dx is b sec theta times tan theta, d theta. Alright, so now here I will have b squared sec squared minus b squared. Then I got my b sec theta tan theta d theta. So the whole idea now is to take out b squared as a common factor. So if I take out b squared as a common factor there, let's see what am I going to be left with. So I took out b squared as a common factor, so I'm left with sec squared theta minus 1, which is exactly what I wanted there. Can you see that? So now, so I got the square root of b squared times, now this is within brackets, so sec squared minus 1 is equal to tan squared. And here I have b sec theta tan theta d theta. Now, there's no plus, there's no minus sign separating, so I can find the square roots. So this is equal to, the square root of b squared is b, the square root of tan squared, remember there's two possibilities, we're only taking the positive, so I'm going with just tan theta. Then I have b times sec theta tan theta d theta. Now it's all about integration. Okay, so this is like revision for integration. So now I'm talking about integration of trigonometric functions. Now you can see you've got tan and sec. So b times b, my constants, b times b will be b squared. Then I got tan times tan, which is going to give me tan squared theta times sec theta d theta. Okay, now how can I integrate it? Okay, so I got tan squared times sec theta. This is not an exact derivative here. Can you see that? It's not an exact derivative. So if I let u equal to 10, the problem is it will not cancel perfectly. Alright. So what can I let u equal to? It's an unusual case now. Okay, then I can do it differently. I can write this as sine squared over cos squared, and then I can write sec as 1 over cos. It can be done that way then. Right. But now what happens if I let u equal to sec? Let's see what happens here. Okay. If I let u equal to sec theta, let's see what happens. Alright. So that du over d theta, the derivative of sec theta is going to be sec theta tan theta. Okay. Now, let's see if it cancels. Right. So I got my b squared there. Now, so this is a good example for you to practice what happens when you have tan squared times sec. So what happens if you let u equal to sec? Du over d theta will be sec times tan. So then I have my tan squared there. And then I have sec theta, which is u. And then I have d theta, which is going to be du divided by sec theta tan theta. Okay. So now, let's see what happens here. Tan squared divided by tan will give me, the sec theta is also, mustn't forget, sec theta is also u. Remember that? U is equal to sec theta, so du over theta, d theta is sec theta, which is u. Same thing. So what happens here now? U and u cancel, tan cancels with tan squared, so you just end up with tan theta, but the problem is that this is du now. Can you see that? That is the problem. So it does not cancel perfectly. Can you see that? So can you get tan theta in terms of u? Let's see. Can you get tan theta in terms of u? So if u is equal to sec theta, let's see what happens. Okay, so we know that u squared is equal to sec squared. We agree with that? U squared is equal to sec squared. So we know that 1 plus tan squared theta is equal to sec squared theta. Okay, that means 1 plus tan squared theta is equal to u squared. So that means tan squared theta is going to equal to u squared minus 1. Yes. But the problem is that this is not tan squared, this is tan now. So that means I'm working backwards now. You can see that if I go and find this tan theta here, I'm going back to the square root of u squared minus 1, which is basically back to where I started here. Can you see that? So if I go and replace this, I'm just showing you as an example what would happen if you let u equal to sec theta. You're going to end up with the square root of u squared minus 1, which is basically back to where you started with. Right. So the option of letting u equal to sec theta doesn't work here. So what do you think will work? Right. You have to try out something to check if it works. Right. Right. So now, what happens if you let u equal to tan theta? Will it cancel? No. What happens if you change it? Let's see. Okay, let's see what happens if you change it. Let's say if you change tan squared to sine squared over cos squared, and then your sec can be written as 1 over cos n. Okay. Now, in a situation like this here, I got my b squared, then here I got sine squared, then I got cos squared times cos, which will be cos to the power 3 d theta. Okay, now here if you remember powers of sine and cos, okay, what did we do when we had sine squared over cos cubed? We would take cos to the top, then I got sine squared times cos to the power minus 3. So option 1, letting u equal to sec, doesn't work. Now look at this option. Sine squared times cos to the power minus 3. Now, remember that when you have an odd power, you split your odd power. Okay. So, can you split up your odd power? Yeah. How many minutes? Let me give you a chance to just do this part of here and see if it's possible. Because what do you have here now? Negative 3. Let me give you 2 minutes just to think about this, because this is power. Okay, forget about the whole substitution thing now. Right, I'm just talking about your trig functions. What would happen now? Let me give you 2 minutes to just think about that. Yeah, I don't know why. It's moving on its own. How many minutes we got remaining there? to continue with this here. Let me just pause what I'm doing. Okay, another class coming in now.